Hello, everybody. I'm going to start you on a new topic. Uh, this topic is in chapter 12, and we're going to start the discussion of curvilinear motion. So we are done with the rectilinear motion, and we also covered the dependent motion. So I want to give you a head start on curvilinear motion. So when we discuss this on Monday, you have seen all the derivations, and we could get started with the projectile motion, hopefully. So let me share my screen with you. Okay, and I'm gonna bring my OneNote, and this section, this topic deals with. So let me write this down: curvilinear motion. Okay, I believe this is section 12.6, if I'm not wrong. You can check on that. I didn't check the syllabi. Guys, you have to excuse me for clearing my voice because of the pollen and the my allergy. So, rectilinear motion was the motion of the particle along a straight path. Now, the particle is traveling along a curved path, like this. Now, there are three coordinate systems that we want to use. So we can describe the velocity and acceleration using three different coordinate systems. Okay. What are these coordinate systems? The first one is called Cartesian. Cartesian means the X, Y, Z. Okay. The second one that we're going to look at that later on in the course is called the normal and tangential coordinate system. Which is totally a different coordinate system denoted by N and T. N for normal and T for tangential. And then finally, we're going to look at the radial and transverse coordinate system. And in particular, a two-dimensional version of it known as polar coordinate system, the R and theta, R for radial, theta for transverse. Today's video and lecture is only dealing with the Cartesian coordinate system, and then an extension of that would be just a two-dimensional XY rectangular coordinate system, which we'll use to describe the motion of a projectile then. Okay, and that should be done next week sometimes. All right, so let me move this down. So this is Cartesian system. So basically, for me to keep track of a particle, let's say if this is X, this is Y, and this is Z, right? And you have a particle traveling along a curved path. How do I keep track of the position of a particle? The best way to keep track of a position of a particle is by keeping its position defined by a position vector R. So R is the position vector. And this R is, let me move this up for you. This R is, in general, has what? Three coordinates: xi plus yj plus zk, right? So it has an x component, y component, and z component. Now, we want to define velocity. What is velocity? Velocity is the rate of change of position vector R, kind of like in rectilinear motion. Remember, we describe position of a particle as R, and then I say, well, let's just call it S. All right, let's go ahead and take the derivative of R. What is R? Again, is xi plus yj plus zk, right? So as we take the derivative of this, keep in mind that we have to use product rule because this is x times I. I is the unit vector along the x-axis. You guys remember from your statics course, right? So we'll take the first derivative dx dt times the second, which is I, plus first, which is x times the derivative of the second. And you might be kind of surprised to see what is the derivative of the unit vector I. We'll talk about that in a minute. All right, keep doing the same thing. So the derivative of the first dy dt times j plus the first, which is y, times the derivative of the second, which is derivative of j with respect to time, and then so on. dz dt, right? The last component times k plus z times the derivative of k with respect to time. So now the question is, what is the derivative of these unit vectors? So for example, di dt, if we do that for I, it would be the same thing for dj dt and dk dt. All right, I is what? I is a unit vector. Its magnitude is equal to 1, right? It's 1 unit. So magnitude is constant. That's a constant, right? And its direction is what? The direction is always along what? The x-axis is a vector that always points along the x-axis. That's I. So the direction is also constant. Direction is also constant. So if you have a vector whose magnitude is constant and direction is constant, then derivative of a constant must be equal to 0. So this guy is 0. Similarly, you could say dj dt is 0, and this guy dk dt is 0. Remember now, you could have a unit vector whose magnitude is constant, but maybe its direction keeps changing as the object moves along the curved path. That would be the case of nt and r theta. We'll see that in the class at some point, guys. Okay? All right, so what happens to the velocity now? After these unit vectors, derivative of the unit vectors are equal to 0. Well, now velocity becomes just dx dt. Well, there may be a better way of saying dx dt is x dot, the dot notation, times I, plus similarly, this guy becomes y dot j, and then finally z dot k, right? So basically, this is the x component of velocity, this is the y component of velocity, and this is the z component of velocity, right? So vx is x dot, vy is y dot, and vz is z dot. You don't have to break it down like that. And if you want to find, so see, velocity in general is going along a curve that has to be always tangent to the path. That's very important, guys. V is always tangent to the path of motion. Okay, so it's something to remember. And if you want to find the magnitude of velocity, then obviously you can take the x component is squared, y component is squared, and z component is squared, right? Like any vector, you can find the magnitude. So this is the magnitude of velocity. We'll look at an example. Actually, I want to show you 3 examples today before we are done with this video. Now, similarly, acceleration is what? The derivative of velocity. So if you go ahead, guys, and take the derivative of what? Velocity. What is velocity? X dot I, right? We just figured out the velocity in the vector form, plus y dot j plus z dot k, right? You already know that you don't have to use really the product rule because the derivative of I with respect to time is 0. So without going through all the additional work, the derivative, so we just do the derivative of the first times the second, and that's it. You just don't do the derivative of di dt, because you know it's going to be 0. So that becomes x double dot, second derivative of x, right, times I. Similarly, y double dot j plus z double dot k. And you already know that this is the x component of acceleration, this must be the y component, and this must be the z component. And if you want the magnitude of acceleration, again, you could do the x component, either put x double dot here squared, y double dot squared, z double dot, or put ax squared plus ay squared plus az squared, take the square root. This would be the magnitude of acceleration, right? But keep in mind, guys, that acceleration in general is not, let's write this down, acceleration vector in general, unlike velocity, which is tangent to the path, in general is not tangent to the path of motion. We'll see. Tangent is not tangent to the path. This will make more sense when we look at the other coordinate systems, guys. All right. So that's it. That's just the description of velocity and acceleration in this coordinate system, Cartesian. Of course, if you have a two-dimensional, just get rid of the z component, right? All right, let's go ahead and look at some examples. So the first example, I'm just going to make up myself. So let's say you have, you're given the motion of a particle, position vector of a particle to be, in terms of time, to be 2t cubed plus 4I plus 6t squared j plus 4t cubed minus 8t squared k. Okay, so basically this is the x, this is the y, and this is the z. Let's say the x, the r is in inches in terms of unit, and t obviously is in seconds. Okay, so let's just make this problem simple. Let's say you want to find magnitude of velocity and acceleration, magnitude of velocity and acceleration at certain time, at t equal 1 second. Okay, so how do you do this? Very simple. You say, look, velocity is the derivative of r, right? So go ahead, take the derivative. You don't even have to break it down into x, y, z. Just take the derivative of this guy. So that becomes 6t squared, that's it, I, plus 12t j plus 12 t squared minus 16t k. That's it. That's your velocity. Let me go ahead and do the acceleration too, and then we do the plugging, guys. Acceleration is the derivative of velocity. Derivative of velocity vector. So take the derivative of this now, right? So what do we get? 12t I, just 12j, and 24t minus 16k, right? Now let's go ahead and plug in t equal 1. At t equal 1, what is velocity? Let's see, velocity becomes 6I, 6 inch per second I. That's the x component. Y component just becomes 12j, and z component looks like becomes minus 4, right? Just make that a minus 4. Okay, that's your velocity vector. I'm going to come back in a second and find the magnitude for you. Similarly, acceleration, just plug in here, t equal 1. Notice that you get 12I. Look at this guy. This guy is no longer a function of time. So it's always 12, the y component of acceleration. And this one becomes 24 minus 16 becomes an 8k. All right, what about the magnitudes of these? No problem. V as the magnitude is square root of 6 squared plus 12 squared plus minus 4 squared. Let me calculate that for you. Let's see, 6 squared, 36 plus 12 squared, 144 plus 16. Take the square root of that. Wow, got lucky, 14. Sometimes you get lucky and you get nice number, I guess. I didn't plan it like that at all, guys. Believe me. All right, what about acceleration? Similarly, this guy squared, this guy squared, this guy squared, 12 squared, 12 squared, 8 squared. 18.76 inch per second squared. So you see, it's very simple, guys. All we had to do, given r as a function of time, right? All we had to do is to take the first derivative, right, of this guy, and then take the second derivative of it, and just plug in t equal 1, or whatever t you were given, and then just find square root of some of the component squared. All right, guys? Now let's look at a couple of problems from the textbook, and that should do it. All right, so I was thinking of problem 1272, and I have actually problem 1272 here for you, so we can use this. All right, it says the velocity of a particle is given by this velocity vector right here, right? Let me just change this to black if I could. All right. So in meters per second. So now velocity is given, which is okay. Remember, if you integrate velocity, you get position. If you differentiate velocity, you get acceleration, where t is in second. If the particle is at the origin at t equals 0, right? At t equals 0, particle is at the origin, which means what? Position is 0, 0, 0. This is x0, y0, z0, if you want to call it. All right. Determine the magnitude of the particle's acceleration when t is equal to 2 seconds. So acceleration magnitude, guys, at t equal to. All right, let's take care of this. This is easy. Look, velocity is what? Velocity is 16t squared I plus 4t cubed j, right? Plus 5t plus 2k. Acceleration is what? Derivative of velocity, guys, right? If you go ahead and take the derivative of this, what do you get? 32t I plus 12t squared j plus 5k. That's it. Go ahead, plug in t equal 2 into this. What do you get? 64i. Let's see, 48j and 5k in meters per second squared. So now magnitude of acceleration becomes what? The square root of 64 squared, just like the problem I showed you a minute ago, right? Take each component, square it, add it, take the square root. I have the answer right here. 80.2 meters per second squared. Okay, so that takes care of determine the magnitude of the particle's acceleration when t equal 2 seconds. No problem. Also, what is the x, y, and z coordinates of position of the particle at this instant? At t equal to, where is the particle? What is the position? Position is r. R is what, guys? R is the integral of velocity. Remember, velocity was the derivative. So this time you integrate velocity. Velocity is what? 16t squared I plus 4t cubed j plus 5t plus 2k. We're integrating this whole thing. Maybe I should put it in a bracket like that. dt. I'm running out of space here, guys. Sorry. dt. All right, no problem. So let me start actually here. So what is r? All right, the integral of 16t squared becomes 16 over 3 t cubed. Be careful, guys. It's a constant of integration. I'll call it C1. This is the x component. All right, the integral of 4t cubed becomes what? T to the 4 plus another constant, C2, j. And finally, the integral of 5t is 2.5t squared, right? Plus the integral of 2 is 2t plus another constant, C3. Okay, that's it. That's your R. So kind of this is your X, this is your Y, and this is your Z now positions. But how do you find C1, C2, and C3? Very easily. Guys, look. At t equals 0, initial positions are what? 0, 0, 0, which actually, if you set X equals 0 and t equals 0, C1 becomes 0, see? C2 becomes 0. And similarly, C3 becomes 0. Otherwise, they become whatever they're supposed to be, whatever these numbers are, okay, if they weren't 0. So look, guys, R becomes now, let me actually give you the answer here. Let me just, R becomes 42.7 if you plug in t equal 2, right? You want to do it at t equal to 42.7 I. This becomes just 16, as you could see. J, remember, C's are 0. And 14K. So at t equal to, coordinate of this guy is what? 42.7, 16, and 14 in meters. Okay? Very simple problem, right? If I'm going too fast, guys, you can always go back and pause, rewind, fast forward, whatever you want to do. All right, let me show you one last problem, and that should be it. So I want you guys to take a look at this video and be ready for Monday class, because I'm not going to spend any time. I'm going to start with the discussion of projectile motion. Maybe I'll just do a quick summary of this. All right, the next problem I want to show you is problem 79. Let me actually bring this problem in front of you so I don't waste your time with the calculations. Okay. It says the particle travels along the path defined by the parabola. You see this particle is traveling along this path defined by this equation, y equal 0.5 x squared. If the component of velocity along the x-axis is given, so look, this problem is a little bit different. V sub x is 5t. Let's erase that. In feet per second. So distances are in feet, time is in second. Where t is in second, determine the particle's distance from the origin, O, and the magnitude of its acceleration. So you want the magnitude of acceleration at t equal 1, that's one thing, and the distance at that instant. So if, let's say, if this was t equal 1 position, that distance from the origin. And look, it again gives you what? The initial position. It says at t equals 0, the particle is right here at the origin. By the way, this is a two-dimensional version. You don't have any z component, as you could see here. You're just using with x, y. Right? You could have done it for x, y, z. But then the equation would be a little bit different, obviously. It's not an equation in terms of y equals something times x squared. All right, look, guys, this is a very simple problem. In order for me to find the acceleration, guys, I need what? I need the x component of acceleration. I need the y component of acceleration. Then I say, oh, the magnitude of acceleration is what? The square root of ax squared plus ay squared, right? That's the magnitude. I can find the x component of acceleration by taking the derivative of the x component of velocity. That's 5. But how could I find the ay? Why don't I do this? Why don't I say x is what? The integral of vx, with respect to time, isn't it? Remember, r now is defined as what? Xi plus yj. V is what? Vxi plus vyj. Acceleration is what? Axi plus ayj. So in this direction, we take the derivative. In the opposite direction, if you have velocity, the x component, in order to find x, you have to integrate, right? That's what I'm doing. So if I go ahead and find the integral, and you'll see why I'm doing this in a minute. What is the integral of that? That's 2.5 t squared plus a constant of integration. But that constant is what? At t equals 0, x is 0, position is 0. Therefore, c becomes 0. So x becomes 2.5 t squared. Why did I get x? Because now y is related to x, guys. Look, y is point, according to the path, 0.5 x squared. So y becomes 0.5 of 2.5 t squared squared. Be careful, guys. So 0.5 times 2.5. 2.5 squared is 6.25. Half of 6.25 is 3.125. And I have t to the power 4 then. Now look, guys. Vy is y dot, right? The derivative of that becomes what? 4 times 3.125, that's 12.5 t cubed. And ay is what? Vy dot or y double dot, right? So that becomes 37.5 t squared. Now I know exactly where the object, the y component of acceleration is, right? And I want it what? At t equal 1. So at t equal 1, this becomes what? 37.5 meters per, these are feet, sorry guys. Feet per second squared. So you already you have the y component, x component of acceleration, which wasn't a function of time, by the way. That was 5 feet per second squared, and you have the y component. So now you know exactly what the magnitude is. Here we go. X component was 5. The y component I just determined for you, 37.5 squared. Let's see what we get here. 37.8, guys. 37.8 is the outcome of this radical. Feet per second squared. This is magnitude of acceleration at this guy. Magnitude of acceleration at t equal 1. All right, so it wasn't that bad. We just have to manipulate the equations a little bit. All right, guys, what about this part? Find the distance. In order for me to find distance between 2 points, I need to have the coordinates, the x, y, z at that time at t equal 1. Well, look, guys, we already have x as a function of time. At t equal 1, x is 2.5 t squared. If you put t equal 1, that's 2.5 feet. What about y? Y is right here. Y is what? 3.125 when you put t equal 1, 1 to the power 4, right? So you're all set. This is 0, 0 position, origin. Now you have gone to what? The 2.5 and 3.125. How do you find the distance between 2 points? Clearly, the difference between the x and the difference between the y, right? You guys remember this from high school? 2.5 minus 0, final minus initial, 3.125 minus 0 also. I was just going to skip that squared, right? Because this is what? This is the 2.5 and this is 3.25, right? And what is the answer? The answer happens to be, let me go back to black. The answer, I have it here. Actually, it comes out to be exactly 4, which is interesting. Nice number. All right, guys. So that's all I wanted to do to get you started on this new topic. Oops, my calculator was falling down. So take a look at this video, please, and go over it. If something doesn't make sense, ask questions on Monday. Okay, guys. I'll see you on Monday. Have a good day and have a nice weekend. All right, let's end this.